Bismillahir Rahmanir Rahim. Assalamu alaikum and welcome to this session. In this session, we are going to talk about operational analysis, which is a framework for analyzing queuing networks without making stochastic assumptions. Up till now, we've been focusing on analyzing queues and network of queues, basically using stochastic techniques in which we model the queue as a continuous time Markov chain, and then we analyze it considering it an ergodic stationary process. So the thing about such assumption is that the results that we get from such analysis only apply at the steady state and only apply if we were to observe the process for infinitely long amount of time. Only then would we say that our results apply precisely and exactly. Also, when we talk of stochastic analysis, it basically applies to an ensemble of realizations. But for any particular realization of a queuing system, we cannot say for certain if our results apply precisely. This led to a problem when we started modeling computer systems using queuing networks, because many of the classical stochastic assumptions of independence, assumption of service distribution being exponential distribution, which is an ideal distribution, but it is fairly difficult to find it in practice that you have exactly an exponential distribution as the service time distribution. So many of these assumptions, especially the assumption of independence, these assumptions are such that they cannot be empirically verified. They can only be disproved, and in fact they have been disproved for many computer systems. And paradoxically, even when the assumptions are all wrong or they're not fulfilled, the results are quite right. So this then forced people into thinking that maybe we can think of a more general framework, a framework which is more general than the framework suggested and created by the work of Markov, Kolmogorov, and Erlang, and all the people who have been working on the stochastic analysis of queuing systems. And people started thinking about making an alternative framework which is operationally testable. So this is a fundamental paradigm change. The idea here is that we should be able to verify all the assumptions that we are making. So, and also the results that we have should apply exactly with very few assumptions to measurements that we can make in finite amount of time. In computer system analysis, we are interested in making measurements over a finite period of time, and we also want confidence that our analysis applies exactly to measurements based on finite time periods. So in a sense, our goal is similar to the goal of physicists when they're trying to find physical laws that are always true, that can be operationally tested. So this kind of analysis is known as operational analysis, and this was created by Jeff Busen in 1970s, and this was then developed by his colleague Peter Denning, and they created an entire framework, and with very few assumptions they went about this business of creating a framework essentially which just assumes that we have job flow balance. So if you have a queuing network, the number of jobs that are coming into the system must be equal to the jobs that go out of the system. And also your queuing network is operationally connected. There is no device that is completely idle. With these very basic assumptions, some operational laws have been derived. And using these operational laws, analysis has been done, which has created compatible formulas to those found in Markovian analysis. So this in fact shows that those Markovian assumptions do produce those results, but to produce those results, those Markovian assumptions are not necessary. And this also explains in part why analytical models have been very successful in modeling computer systems. It has been shown time and again that all the assumptions that we have are not met. The processes are not stationary, the jobs, the packets are not independent, but still the results are fairly accurate. It is because we can also get the same results from more general assumptions. And that is the idea of today's session. First of all, to introduce the notion of operational analysis, and then to create operational laws. Laws that are always true. Laws like the physical laws that physicists have, like Newton's law. The laws of electricity, like the Ohm's law. So we have V is equal to IR. That is always true without making recourse to the assumption that V or I or R is a stochastic random variable, and we are working with expectation of this. So we are thinking of an ensemble of realizations, and we say that this is what we expect, but for any particular measurement, we cannot say anything for certain. But we are interested in results that apply precisely. So that is the basis and preamble of today's session. And from now, I'm going to start my discussion on operational laws, which are laws like, as mentioned, Ohm's law, for example. These are laws that are always true, and they apply very, very generally to a very broad class of systems with very, very few assumptions. In particular, we don't make any assumptions that we cannot operationally test. We do not assume exponential service distributions. We do not assume Poisson distributions. We do not assume independence. We only assume job flow balance, something that can be measured. We can measure the number of arrivals and the number of completions. If both of them are the same, then we have job flow balance. And if that is met, our results are apply very precisely. So just to get a feel of operational variables, let me define a few variables for you. So we see on the slide 4 variables defined. These are all operational variables, things that we can measure. The first variable is T, which is the measurement interval total time. Obviously, this is something measurable. The number of arrivals is represented by the letter capital A. The number of completions is capital C. The system busy time is capital B. The idea I want to tell you is that while this session may look formidable because we have lots of notation, and unfortunately in studying queuing theory, we have to not only study a lot of notation, but also see that many of the notations are confusing. Sometimes you have new notations for the same thing. But this thing is very simple, and this may be rightly called as queuing theory light, because this is making a complex theory very simple. Not light in the sense that it is light in theory, but in light in complexity. So we have just defined 4 operational variables, things that we can measure, and from these we can derive some important parameters of interest. We define utilization to be busy time divided by total time. So this makes sense. Amount of time you're busy of the total time is the amount of utilization of that device. The throughput is just the completions over total time, C over T. The service time is the busy time divided by the number of completions. So B over C is equal to the service time, the time it takes to service one completion. Arrival rate is the number of arrivals divided by the total time, or it's equal to A over T. We typically make the assumption in operational analysis that the arrival rate is the same as the departure rate. So arrival rate is the same as the throughput. Also, we can alternatively say that the number of arrivals are equal to the number of completions. We note here that for all of these operational variables, if we have a subscript, that typically refers to a device of the overall system of multiple devices. So for example, if I have C of I, that tells me that this is the completion of the ith device. If I don't have a subscript, or if I have 0 as the subscript, then that is the system level operational variable. To get a feel of these operational variables, it is advised that you do examples of your own, but we'll see just an example of what we've defined, but it is very important that you also exercise on your own. So assume that arrival rate is given to be 2500 packets. The number of completions are also 2500 packets. the time period over which observation is made is 500 seconds. And of this 500 seconds, the device was found to be or measured to be busy for 300 seconds. What can we answer for this system? We see that we can answer many things that would not be apparent or obvious if we were not aware of these formulas. While these formulas are very simple, but they actually also point out to you something that you may miss if you were not thinking deeply about these things. So utilization is just B over T, and it's found to be 60%. Throughput is just 5 packets per second. We also find that the arrivals are equal to the completions, and therefore our findings would apply precisely. The service rate is equal to B over C, and it is determined to be 5 packets per second. Okay, let me now show you a few things so that we can then understand the operational laws that we derive using the standard operational analysis techniques. So first of all, let me show you an open queuing network model in which arrivals come from outside the system. They go to different devices of the system, and then after taking service, they eventually depart. We make the assumption that the number of arrivals are equal to the number of completions. And the queuing network that we see on the slide now is known as the central server model. The external arrivals always come at the server, CPU server. This is the central server in this case. And then this job is routed to various devices for service. It may be that this job is routed to different devices multiple times for service. And after the entire job is completed, it would go out of the system. So every time the incoming arrival from outside the system comes to the CPU, it goes to some device, comes back to the CPU, goes back to some other device possibly, and this going back and forth happens for a while before the job completes and the job can exit the system. So we make the assumption that we have job flow balance. This is important for operational analysis. Okay, now we can define something known as a visit count. So if we have a central service model, a job comes from outside this network to this network, which is modeling a computer system having a CPU and multiple different resources. This job will come to the CPU first, but it will also go to other devices possibly and also go to them multiple times. So visit count essentially measures that for every job on average, how many visits is it making to different devices. So typically you would find that the visit count of the CPU is the highest because all the arrivals are coming from the outside to the CPU, and from the CPU things get routed to different devices. And after getting service at those devices, they come back to the CPU, and this thing happens for a while until the requirements of the job is completed, and at that time it can be sent out of the system. So you also see that the visit count of CPU as shown on the screen is equal to the visit count of all the other devices of V2, V3 and V4 plus 1. And this plus 1 is for the first job that comes from the outside. This is true for the central server model. So if you recall, this is a model proposed by Busen to model multi-programming systems. We also have other models. So for those models, the interpretation and the calculation of visit count would be different. But for now, just remember that if a job comes from outside and comes into the system, visit count tells us how many visits on average would it be making to various different devices. Okay, from here we can also proceed and talk about the service time and the response time of this system. The service time is the time it takes to service particular requests that come to particular devices. So for example, an external arrival comes to the CPU, it is sent to the, let's say, the disk device, and then it performs some service there. The time it takes on average to service a request is known as the service time. And this is in general different for different devices. So we index this by a subscript. So we have S of I, which is the service time required per visit at the device I. We can also talk of the response time, and the response time refers to the entire system, which in turn is composed in this case of the CPU and all the other devices. The total system response time measures the entire time spent inside the system. We can also talk about the device and the system's throughput. In general, the device throughput is assumed equal to the arrival rate due to the job flow balance, but it is not necessary that the device throughput also be the same as the system throughput, because it is possible that a job would come into the system and it would require more number of completions on the various devices inside the system. So in this case, the system throughput would be less, but the device throughput would be more. So we would see, in fact, that there is a relationship that relates the system throughput with the device throughput. And that relationship basically also incorporates into the picture the number of visits to those devices. So essentially, the device throughput is equal to the system throughput multiplied by the visit count. And that makes intuitive sense, because for every job that is completed, you're sending multiple jobs to those devices. So those throughputs must be greater in ratio of the number of visits that are sent their way. Okay, we have defined the service time for various devices, but these service times are performed for every visit. But in general, a job that comes into the system does not go onto these devices just once. So in essence, it actually goes to these devices according to the visit count. So from that, we can determine the total service demand, which measures that for every job, how much time typically is spent on the different devices. So we calculate the service demand as the service time multiplied by the visit count to that particular device. Everything that we've covered is very basic, and it does not make any strong assumptions. So these are all things that we can measure, and then after describing all of these things, we're going to discover laws that must be true if the job flow balance is maintained. Lastly, up till now, I have been talking about open queuing networks. We also have closed queuing networks in which there are fixed number of jobs that are circulating. So there is no external arrival. So the right way of characterizing such system then becomes defining the number of jobs in the system. And this thing is defined by the variable n. Also, we can think of the closed system or the closed queuing network in which we also have terminals. And because terminals are manned by humans who have variable input rate, we can model the system in a sense that the terminals can be classified into two kinds. So they may be in two states. They may be either in the thinking state or they may be in the waiting state. When a terminal is in the thinking state, the human who is connected to the terminal is thinking of what command to send to the CPU. And if it has sent the command, then it waits for the completion of the command. So in this sense, we can model the terminal, and we represent the average think time as the capital Z letter, and also the time we usually wait to receive response per transaction, we denote that by capital R. And the rate of making the transitions from the thinking state to the waiting state is controlled by the system throughput. And in fact, we would make this precise when we discover a law which is known as interactive response time law, which basically addresses this question, that what is the relationship of the number of jobs and these parameters R and Z in a system in which we have these terminals. So now we have enough notation to start talking about operational laws. And as mentioned before, operational laws are simple relationships that are empirically verifiable, and they make very few assumptions, and they have multi-purposes. The first purpose may be that it helps you calculate variables that you can calculate in principle, But because you know this relationship, you can actually calculate it without actually making the measurement, because the operational laws are true if the very minor assumption that we have job flow balance is met, then our measurement would also be applicable precisely. We can also make what-if analysis using these laws, that we know how these operational variables are related. We can then very easily see that, okay, what will happen if we change this operational variable in this way? And this then allows us very quick evaluation of various different options. So let's start by talking about the first law, the first operational law that we'll be covering. This law is known as the utilization law. It's a very simple relationship like all the laws that we'll be covering today. You would find that operational analysis is very simple. It makes very few assumptions, and the formulas that we have here are less intimidating and less complex than what you had for stochastic analysis. So the hard part is gone, and now you have the easy part. So for the utilization law, we make the observation that the utilization of any device, which we represent as U of I, is equal to the time it is busy over the total time. So we can express it as Bi over T. We also note that the throughput of the ith service center is equal to the number of completions divided by capital T. Lastly, we observe that S of I, the service time of the ith service center, is equal to Bi over Ci. Now, if we relate all three of these things, we find that Ui is equal to Xi Si. So we have a straight relationship, which may not be obvious at first sight, but now that we have rearranged things and we've seen that what Ui is expressed as, what Xi is and what Si is, we know that this must be true, because these are all operationally measured variables. This relationship is mathematically true in all cases if job flow balance is maintained. From this, we can also find out the throughput of ith device, and that is determined by the ratio of Ui and Si. Again, this is something that may not be intuitively obvious, but making these simple algebraic manipulations, we've come up at a law which helps us determine one of these variables if the other two are known. So, as mentioned before, these laws are very useful for calculation, consistency checking, and prediction of performance measures. What do we mean by consistency checking? If we have measurements that do not match with these laws, then it is perhaps the case that our measurement is faulty, because these laws are always true, and as shown, because these are simple operational variables, and as expressed here, Ui is equal to Xi Si, this thing must always be true. And if your measurements are such that they do not match with this, then it is basically a sanity check. It allows you to discover that there may be problems in your data. As an example of utilization law, let's consider a network gateway at which packets arrive at a rate of 125 packets per second, and the gateway takes an average of 2 milliseconds to forward them. Can we calculate utilization of this device based on just this information? Yes, we can. Using the utilization law, we first of all note down the information that is given. So the arrival at the rate of 125 packets per second is the same as the throughput because of the job flow balance. We're assuming that the arrival rate is the same as the exit rate. So we have X of I given. We also have S of I given, because the 2 milliseconds that it takes to forward those packets is precisely the service time. So we have both Xi and Si, and then it's trivial from this to calculate U of I, which we determine to be 25%. So while this may look very plain and very obvious to you, let us now highlight the remarkable property of this utilization law. The remarkable property is that we have not assumed any service distribution. We have not assumed any arrival distribution. We have not assumed independence or any of the other standard assumptions like the system approaching steady state behavior. But still, using operational analysis, we get this utilization value, which is the same that we would have gotten if we had made those Markovian standard stochastic assumptions. So that actually tells us that this answer does not need those assumptions. This applies very generally, and having the operational analysis framework allows us to discover this. So the next law that we are going to cover is a generalization of utilizations law, and it is something that you would be aware of. It's a fundamental result in network performance evaluation in analytical modeling. It is the Little's law, something that we've covered before, but what we did earlier was the stochastic version of this. Now we are going to see that Little's law also applies in the sense of operational analysis. It also applies to operational variables, and we would see how that actually works out. So first of all, let me point out that there is a change of notation. Earlier we had described Little's law as n is equal to lambda r. In fact, we had expressed it in terms of expected values. Expected value of n was equal to lambda multiplied by the expected value of r. Because in that case, we were assuming that these are stochastic random variables, and we could only make statements about an ensemble of realizations. We can only talk about mathematical expectation. But now we have operational variables that are empirically observed and measured. We see that Little's law applies to this case as well. In this case, we represent the n variable, the expected number of customers in the system, or the mean number of jobs in a device. If we think in the context of computer systems, we represent it by Q of I, which is the number of jobs in the ith device. Also, we have X of I here, which is just the equivalent of lambda that we had for stochastic version of Little's law. And these two are equivalent because we know that due to job flow balance, X of I is the same as basically lambda I, the arrival rate. And lastly, R of I is the mean time in device. So you would also note that I'm changing the terminology to a more computer systems perspective. Earlier we were talking of customers in a queue, which was really specific to operational analysis. But now we can talk specifically about computer systems, and now customers would be jobs, they would be packets, and accordingly we make the distinctions. So the remarkable property of Little's law is that it applies very generally. So this Qi is equal to Xi Ri applies at the level of just the number of customers that are in service. So that is effectively just a part of the device. So we're excluding the number of jobs that are queuing up for service. We can apply Little's law to that part as well. We can apply Little's law to the device. So if you have a queuing network, you have, for example, CPU, disks, and memory, you can apply Little's law to one device. You can apply Little's law to the entire system, and you can also apply it to a system that includes the terminal. More about this just a little while later. Let me tell you how we derived Qi is equal to Xi Ri, and I refer you to our discussion on the fundamentals of queuing theory, in which we talked of Little's law and its derivation. I'm just going to very briefly sketch out what was the derivation about. So what we are interested in measuring is the mean queue length, but the queue length, which includes the customer in service, is something that is variable. So if you look up some device, the number of jobs it has varies, but we're interested in average values. So we can express and determine this mean number of jobs in a device by the use of two averages. The first average is Q, which is the mean number of items in a device, and also R, which is the mean time in that device. And we show that the instantaneous queue length, which is shown the leftmost in the three graphs that we see on the slide, is equivalent to Q into T, where Q is the average queue length including job and service, and capital T is the complete time. And it is equivalent to C into R, where R is the average response time. From this, we can straight away see that Q is equal to XR, and idea applies that the mean number of jobs in a system is equal to the throughput of that device and multiplied by the mean response time. And this applies to many different levels of generalization. Let me show you how general this can be. So if you have a central server model, you would have CPU, you would have multiple disks, you would have multiple terminals. So you can apply Little's law just to a single disk excluding the queue. So this is effectively just part of a device. You can also apply it to the entire device, and the interpretation of Q, R and X would be defined accordingly. We can also talk of the entire system in which you have the CPU and the many different devices, and we can also incorporate the terminals inside this framework and still use Little's law, which is really remarkable. This is a very simple result, and it applies across the board at many different levels of generalizations. Let us now do a couple of examples of Little's law. So the first example, we're going to see the average delay is given, and it is experienced by a packet when traversing a network segment, and it is given to be 50 milliseconds. The average number of packets that cross the network per second is also given, and this is the network throughput. This is equal to 512 packets per second. So in this case, our black box that we're considering and applying Little's law to is the entire network segment. So the number of packets in this network segment must be equal to the throughput multiplied by the average delay. And when we take the product of these two things, we determine the average number of packets to be 25.6 packets. Okay, let's see another example of Little's law, except that now it is really the utilization's law. But now we are basically applying Little's law just to the server part of a device, excluding the queue. So the question is that the disk of a web server receives requests at the rate of 20 requests per second. So this is the arrival rate. So we express this as lambda disk is equal to 20. The average disk service time considering both random and sequential request is 8.02 milliseconds. This then is S of basically the request, the service time used to service the request, and this is 8.02 milliseconds. What is the average disk utilization? We can still make use of Little's law, but now our black box is not the entire system, which includes the CPU and the disk. It is just the disk. So making use of job flow balance, we know the arrivals we can determine from the arrival rate, the throughput, which is 20 requests per second. We also know the service time. So we have all we need to apply utilization law, and we determine from this that the utilization of the disk is 16.04%. So let us now again look at this and realize that utilization law is just a special case of Little's law when it is applied to a server facility excluding the queue. So from that, the number that we get is basically how many customers or jobs do you expect to see at the server at any random time, and that essentially is utilization. Okay, now we have up till now derived two important laws. The first law was utilization law, and then from that we generalized to Little's law. We are going to cover some more cases, some more special cases of Little's law, but before that we also need to uncover some more laws. So one law that we'd be doing now is known as the forced flow law. It's again a very simple law that relates the system throughput to the device throughput. So assume that we represent the system throughput by capital X and the device throughput by X of I. then we have a very simple relationship that x of I is equal to x vi, which is very intuitive, and in fact we did this in passing at the beginning of this lecture, that the device throughput must be equal to the system throughput multiplied by the number of visits a job typically makes to a device. So it can be proven if we observe that system throughput x is equal to c over t and device throughput is equal to c of I over t. So if we make some rearrangements, we see that this is exactly equal to x into vi, which is the law that we want to arrive at. As an example of this, consider a device that is shown. It has a visit count of 4 and the arrival rate is 2, and we are asked to calculate the device throughput. So the system throughput is not explicitly given, but because of job flow balance we can determine that if the arrival rate is 2, then the throughput must also be 2. So the system throughput then is 2. So we have 2 jobs completing per second. But for every job we're sending 4 requests to device K, and therefore the throughput of device K must be equal to 8, which is the product of 2 into 4, which is again very simple, very intuitive and easy to understand. Let's now generalize from the Little's law and derive the system level response time. So if we apply Little's law now to the system, with the interpretation that this is being applied to the system, we have from Little's law Q is equal to XR. So if this thing is applied to the system, Q is the total number of jobs in the system, X is the system throughput, and R is the system response time. So we make note of the fact that the total number of the jobs in the system would be the number of jobs at all the devices. So capital Q may be written as Q of 1 plus Q of 2 all the way for all the M devices that we have in the entire system. So if that is the case, and we know we make use of Little's law, we can write Q as X into R, and we can write Q of 1 as X1 R1, and similarly for all the other M devices. So from that, making use of forced flow law, we've just discovered that we have a relationship that we can use to relate the system and device throughput, which is simply that xi is equal to xvi. So every time you have some device throughput, we are going to translate that into the product of the system throughput and the visit ratio of that device. So x1 becomes xv1, x2 becomes xv2, xm becomes xvm. So you have x common on both sides, and from that we can discover the system level response time, and it is just the sum of the response times at individual devices weighted by the visit counts. So if you have some job visiting a particular device twice, for every job that response time is multiplied by 2, and so on. So essentially the system level response time R can be expressed as the summation of I is equal to 1 till capital M, where capital M is the number of devices that you have in the system, Ri Vi. Ri is the device level response time, and Vi is the visit count to that particular device, device I. So this is the general response time law. From this we can determine the system level response time, knowing the individual response time at the different devices and the visit counts to those devices. Let's consider an example to make this thing more concrete. So for a time sharing system, assume the following values for device level visit counts and response time. So we have 3 devices, CPU, and let's say we have 2 disks labeled A and B. For each of these 3 devices, we have the visit counts as well as the device response times. So we observe again that vCPU is equal to VA plus VB plus 1. So this is the central server model. We also have the response time for each of the devices. It is very easy to calculate the system response time from this. It is just equal to the product of R CPU, V CPU, and we add to that RA, VA, and we add to that RB, VB, and this thing comes out to be 68.6. So again, very straightforward, but very, very effective. If we have a system in which we also have terminals, then things become a little more complex. So we need to again modify our interpretation of what then is the response time of the system that includes the terminal. So as mentioned before, the terminals can be in two states. They can be conceptualized as either thinkers or waiters. When in thinking mode, the terminal or the user at the terminal is thinking of what command to issue. And when the user is in waiting mode, he is actually waiting for the job to complete so that he may then go into the thinking mode and then issue another job. So with this interpretation, we can model the interactive computer system as shown on the right hand side of your slide now. You see that we are characterizing the system in two operational variables, and these are N and Z. N is the number of users, also the number of terminals that we have, and Z is the average think time. And these users, they continually cycle around between these two states of being in thinking state and being in the waiting state. So the overall response time of the system can be thought of as R plus Z. Accordingly, if we apply Little's law to the entire system, including the terminals, we would see that the version of Little's law applied to this level of generality is N is equal to X into R plus Z. So from this, if we solve for R, we get what is known as interactive response time law. It can be expressed in the form of this equation: R is equal to N over X minus Z. Alternatively, we also have an expression for X, and that is equal to N over R plus Z. So let us now do an example of interactive response time law. So suppose that 50 workstations are served by a single file server. Each workstation computes for an average of 0.5 seconds between server requests. The server handles 80 requests per second. What is the server response time? So the first thing we need to note here that in this example we have interactive workstations that have some think time. And that think time is given as Z is equal to 0.5 seconds in this case. We also have 50 workstations, so we can make note of this and express this as N is equal to 50. We also are given that the server handles 80 requests per second. So this is the throughput. So from this, we have all the variables that are needed to get the value of R. Using the interactive response time law, that is R is equal to N over X minus Z, we get that the system response time would be equal to 0.125 seconds. So this then illustrates the power of interactive response time law. Even when we have terminals that have some think time, and we can still model it using an operational law. Okay, finally, let me give you the final operational law that we'll be discussing today. This is the service demand law, and it is as simple as all the other laws. It is simply the usage of utilization law and the forced flow law to find a more convenient form in which instead of having S of I, we'd be having the service demand of that device. The other important point here is that now we express U of I as a function of the system throughput. So if we know the system throughput and the average, we know the service demand of a particular device, we can calculate the utilization of that device. This follows from the utilization law, which is UI is equal to XI SI. Make note that in this case we have the device level throughput. The other thing that we'd be using is that XI can be decomposed into X into VI, and from that we make use of the fact that VI SI can be written as DI, which is the demand that is placed by the entire job, which goes to that device multiple times. So we're incorporating the visit count along with the service time to calculate the overall service required by a particular job. So this is convenient because now we have a relation between UI and the system level throughput. Let's do an example to see this. We are given that the visit count of the device K is 4. The arrival rate is equal to 2. So from the arrival rate, we know from the job flow balance that the throughput must also be 2. And we are also given the service time of this device K. So S of K is equal to 0.025. From that, we can calculate by multiplying the service time by the number of visits to this device to calculate the overall service demand, which is D of K, and this is equal to 0.1. So U of K then can be calculated in two different ways. So depending on what thing is easily measurable, we can calculate U of I either as a function of the system level throughput or as a function of the device level throughput. So now to encapsulate everything that we studied and to give an overall view of this, let me again recap and let me show you that how all these operational laws actually are following more or less from Little's law. So if you remember Little's law, extension of Little's law to these particular cases should be quite easy. So Little's law can be expressed only at the service center, excluding the queue. So this is precisely the utilization law, because when Little's law is applied at this level of generality, then our interpretation of N and R change to these values. We can also apply Little's law to an entire device, including the queue, and that is the Little's law that we are commonly familiar with. It can also be applied to the entire system containing multiple devices, and from that we can make note of the fact that the mean number of jobs in the system is equal to the number of jobs at all the different devices, and from that we can calculate the response time law, the general response time law, which relates the system level response time to the device level response times. Finally, we can apply Little's law to the entire system, including the terminals, and in this case we express this law in the equality that R is equal to N over X minus Z, but this really follows from Little's law. So I hope that you can find how these laws are related. To wrap things up, let me also tell you a very important additional information that follows from service demand law, and that is that we know that UI is equal to XDI. In other words, the utilization of a device is equal to the system throughput multiplied by the service demand of that device. So what does this mean? This means that from this we can determine the bottleneck device of the entire network. Because if we have an entire network, it is only as fast as the slowest device of this network can allow you to be. Because any device cannot have more than 100% utilization. So from UI is equal to XDI, we know that the system level throughput would be a constant. So from that it follows that UI is proportional to DI. So the device in your entire queuing network that has the highest service demand is your bottleneck device. And from this we can determine the maximum throughput your queuing network can achieve. And that is following from the properties of the bottleneck device. The word bottleneck actually follows from the fact that the outgoing flow of a bottle is limited by its narrowest part. Similarly, if you have a queuing network, the maximum throughput that we can have is limited by the slowest device in the queuing network. Okay, so we have covered lots of ground. The things are simple, but because we have introduced a lot of notation, they may be intimidating at first. But if you can understand this lecture, you will inshallah find that it applies very widely and broadly to practical problems. So I hope that you find this useful. For your convenience, I have tabulated all the notation as well as all the laws here. We talked of the utilization law, the service demand law, we talked of the Little's law, the interactive response time law, and the forced flow law. All of them are noted down on this slide. So it's time now for me to conclude this session. I'll conclude by stating that operational analysis is an extremely important technique or a set of techniques, and it is complementary to stochastic queuing theory. It does not replace it, but using this we can understand queuing networks better. And because this entire framework was created by computer scientists, many of the important features of this operational analysis actually follows from the needs of computer scientists to model computer systems and computer networks. So it is very useful for us and very important for us to understand operational analysis. And if we understand this, you would find that you would be able to solve many practical problems using these simple laws. So we also saw that operational laws are like physical laws that apply very generally without restriction, making very few assumptions, and they are operationally testable. That's the entire edifice on the basis of which the framework of operational analysis is built, that everything should be testable and measurable. We don't want to make any assumptions that cannot be tested. So that would be the end of today's session. I'll see you next time, inshallah. Assalamu alaikum wa rahmatullah.